Okay, the first thing we want to get down with logarithmic functions and equations is, what does it mean when you see log or ln in an expression? So first off, we could think of something that's real familiar to us, like 2 to the third equals 8, and that, of course, expresses kind of the result of having 3 factors of 2. If you take 3 factors of 2, multiplication gives you 8. The question becomes something like, what if you wanted to know how many factors of 2 it would take to get you a number like 11, something that's not simply a power of 2? Well, the expression 2 to the third equals 8 can be written logarithmically as saying log base 2 of the number 8 is 3. So you can see the focus shifts here to knowing the result and knowing what the base is and wondering what the exponent is that's required to turn this number 2 into an 8. Whereas here, you know the base, you know how many factors it's going to be, and the only question is what are you going to get when you multiply 3 factors of 2, and the answer is 8. So that seems kind of trivial. This is a little bit more challenging, because if you use that idea and you say, okay, well, log base 2 of 11, which is what this would equate to, what power is required to turn a 2 into an 11? 2, how many factors of 2 do you have to multiply to get 11? Intuitively, you'd know that it has to be more than 3, because 2 to the third is 8, but it can't be as big as 4, because 2 to the fourth is 16. So we kind of have this idea that when you see a log expression, you look at the base, and you say, okay, that base raised to this answer exponent will get you this number. And of course, we don't know that off the top of our head, but the calculator does for us. So we can ask the calculator log base 2 of 11, and it'll spit out a decimal for us, which would be exactly the same as if you just said, okay, well, let's go graph 2 to the x, which would look like that, and then graph y equals 11, and see where they cross. 2 to the x, when is it equal to 11? And it would give you some value, like we said, somewhere between 3 and 4. So that's basically what a log expression is telling you. It's telling you what the exponent is. Now, when you look at logarithmic functions, you get something like y equals log base, I should usually use b, of x. And a couple things you need to know. This domain here of whatever you're taking the log of essentially is whatever's in those parentheses has to be greater than 0. So very, you kind of hope for some straightforward questions about what the domain of this function is. So if we have y equals, or f of x equals log base 3 of 2x minus 5 plus 1, that's a logarithmic equation function that's been shifted up 1. That shifting up 1 has nothing to do with the domain. The domain goes right here, and you just say, okay, well, 2x minus 5 has to be greater than 0, so 2x has to be greater than 5, so x has to be greater than 5 halves. So interval notation might look something like 5 halves to positive infinity. Notice the use of the soft bracket, indicating that 5 halves is not part of the domain. It has to be greater than 5 halves. So very straightforward. That's one of the first, kind of primary questions that you can always be asked about logs is what's the domain of a function? And you just set the quantity that's being logged, if you will, greater than 0 and solve. So now we're going to go into these properties of logs, which are lifesavers in some advanced mathematics, the things that you can do with logarithmic expressions to rearrange them and rewrite them. The first one we have here is this log of a product, and I just did a generic, log base b and xy. We'll do some specifics in a little bit, but the translation here is that you can take the log of a product and represent it as the sum of 2 separate logs. And essentially what you're doing is you're saying, okay, if I multiply 2 things with the same base, I wind up adding the exponents. That's basically what this translates to. The next property is a log of a quotient, and intuitively you might guess that it's going to be the log of the numerator minus the log of the denominator. And again, we'll see an example of that shortly, but that goes very intuitive based on the first one. And then lastly, this one that's really magical that helped us in solving exponential equations. the fact that if you have a log of a quantity that's being raised to a power, you can take that power and bring it down in front and do multiplication. And this becomes n times log base b of x. And this has the idea of if you're taking a power to a power, you wind up multiplying those two powers. So I'll just give you a quick little example of how each of these things can be used. Sometimes they're used going this direction. You have a log of a product and you have to break it into a sum, but more often you have a log of a sum and you have to condense it down to a single log, because in solving log equations, generally the strategy is if you have log expressions mixed in with constants, you want to isolate the log expression. So we might have something as simple as log base 5 of x minus 1 equals 3. This is an example where the log expression is isolated already. There's a log expression and there's a constant. And if you can get your log equation to look this way, it's going to be real easy to solve, because you just use my little mantra of the base, which is 5, raised to the answer, which is 3, equals what you're taking the log of. And now, piece of cake, all you have to do is add 1 to both sides. 5 to the third is 125, equals x minus 1, so x, of course, is going to be 126. Now, that gets a little more challenging if your log expression is not already isolated. So you could have something like the log of x plus 2, let's say minus log of, I don't know, x equals 5. Yeah, let's not say 5, let's say something like 2. So now what we're going to do is say, okay, this log equation has the difference of two logs, which we saw up here. So the easiest thing we can do is take those two separate log expressions and condense them down to one, and we'll get something like log of x plus 2 over x, and that's equal to 2. And now, I didn't mention it, but this is a common log. When there's no base explicitly expressed, you can assume that there's a 10 there, so I'm going to go ahead and put a little 10 in there just to remind us that that is our base, and now we can use our mantra that the base raised to the answer equals what you're taking the log of. So just think about both sides being fractions, and you can cross multiply. So x times 10 squared is 100x, and then 1 times x plus 2, of course, is x plus 2. Get your x's together, you have 99x's equals 2, so x equals 2 over 99. And that's a really, really common type of log equation, something basic like that. And that's something you would certainly expect to come across. Okay, just throwing at you another example of how you can condense a log expression to get it down a little bit simpler. So I'm going to combine two of our rules here where we have a product of a constant times a log expression, and then the sum of two log expressions, maybe in the big picture, and then each one of those involve a product of a constant and a log, constant and a log. So we're going to use our power rule in reverse, and we're going to say, okay, this 5 that's down in front can go up and be the power associated with x squared and y cubed. So we could rewrite this as x squared y cubed being raised to the 5th, and we're taking the ln of that stuff. And of course this 2, we can do the same thing. We're adding the ln of xy cubed, and that's being squared, and we're taking the ln of all that stuff. Now we can just apply when you take a power up to a power, you multiply those exponents. So we'd have the ln of x to the 10th and y to the 15th. And then over here we have the ln of x squared and y to the 6th. And now that we have this sum of two log expressions, we can condense that to the ln of the product of those two things. So we're really looking at the ln of x to the 10th, y to the 15th times x squared and y to the 6th. And then of course we have got some like bases here with the x's and the y's, and we can just condense those guys down into x to the 12th with the x to the 10th and x squared, and then y to the 15th and 6th makes y to the 21. So that would be your final answer there. very common, typical like homework type question, just applying the product and power rules for logs. Now here's one that looks maybe a little bit more intimidating. We've got a log of a quotient, and this time I'm going to expand this one. This has a fifth root of x over a fifth root of y. Now it's no coincidence I did a fifth root of both of those things, which we could think about a couple of ways. We could use our properties of x or of radicals and say that's the ln of the fifth root of x over y, because as long as you have the same root with two different radicands, if you will, we could combine those two guys underneath one fifth root. However, doing that, it's nice to remember that a fifth root is like a 1/5 as a power, so this could be x over y being raised to the 1/5 power, and we're taking the ln of that. So we could take that 1/5 down in front, say it's 1/5 of the ln of x over y, and then use our quotient rule and expand that and say, okay, this is 1/5 of the ln of the difference, the difference of the ln of x and ln of y. And now we've taken a single log expression, and broken it up into two separate log expressions. So again, that's just examples of how you can go both ways with logs, making a single expression expanded or an expanded expression condensed down to a single log. Lastly, with these properties of logs is, again, a little bit of an idea of remembering that a log represents an exponent. So if we had something like the ln of e to the third power and how that would reduce, I always said it's kind of like putting training wheels on to write ln as log base e, because it helps you realize what the question that's being asked. You say, okay, ln of e cubed means log base e of e cubed, which is asking the question, what power do we raise e to get this argument being e to the third? And now it becomes pretty obvious. Oh, of course, it's the third power that would raise e to get e to the third. So after you do a little bit of this and you understand it, you say, okay, well, whenever I'm ln'ing e to the something, those two operations just kind of kill each other. So if you have the ln of e to the seventh, the answer is just 7. And it doesn't take too long to convince yourself of that if you go through these steps. Of course, that could look a little bit more scary if you did something like the ln of the third root of e to the fifth. Well, now you'd have to recognize that the third root of e to the fifth is ln of e to the 5/3 power. And now you can recognize that the ln and the e are going to kill each other, and we get 5/3 as our answer. So that's nice to get those properties. That kind of works in reverse as well. If you have an exponential expression that involves a log in it. So let's say we have something like 7 raised up to the log base 7 of 49. Now, just to be clear, that entire log expression is an exponent. It both is an exponent to the 7, but again, it represents an exponent. So you can figure this out. This exponential expression here, this log base 7 of 49, is asking what power do you raise 7 to get 49? And of course that answer is 2. But what are we doing with that 2? That 2 is the power that we're raising 7 to. So our answer is 49. So you might say, wait, I saw 49 a minute ago and it was right there. And that's exactly what is always going to happen if this quantity and this quantity are the same. If the base of the big expression and the base of the log expression are the same, those two operations kill each other. Taking 7 and raising it to some power, and if that power is a log base 7, those two things just kind of cancel each other out and you're left with 49. So for example, in general, log base b of x, if b is being raised up to that power, the answer is just x. So those two things cancel each other out. Again, just a nice, useful little shortcut. And I just want to add on a little bit here with logarithmic functions. Kind of one of the natural extensions of both logarithms and exponentials is the study of logistic functions. Now we just did this for a little while in our pre-calc class, But these are the functions that give you a graph that might look something like this, where it has horizontal asymptotes on both ends. This thing is going to go towards 0 on the left, and it's going to level out somewhere on the right side as x goes toward positive infinity. This graph's going to level off at a horizontal asymptote. Now, the template for these things looks a little intimidating with this c over 1 plus a times e to the negative kt. It's not that bad. The real main thing you need to know is this numerator, this c value, is the limit to growth. So if you see a function such as y equals 500, for example, over 1 plus, let's say, 400 e to the negative, let's say 0.7 t. This thing is going to have an initial value that would occur when t is 0. If you think of t being 0 in this equation, that's going to make e to the 0, which is going to make 1, and you're going to have 500 over 400 plus 1, which would be about 500 over 400, which is about 1.25. So this thing, when x is 0, is going to be around 1.25. Now this thing's going to grow and then eventually level off at 500 up here. So a common question here is simply just what value of t would it take for us to get to, say, 400 or 300 for a y value. And probably the best way to do that is just, let's say you wanted to know when is this thing going to reach 300. Well, we would just do a graph of y equals 300 and then see where this thing crosses. So let's look at the calculator for that. So again, the key to using the calculator on these things is knowing, a little bit before you go in what these values mean. This 500 is going to be our limit to growth, so I set my y minimum at 0 and my y max at 500. Not really knowing how long this is going to take, I can just look at that and know exactly how this thing's going to behave, other than it's going to have this general shape. I just, set a t value at I think I did something like 0 to 20 to get started. If it didn't intersect by that time, you would just expand the t value. But 0 to 20 turned out to give me a pretty good graph, and it turned out the intersection occurs at a t value, or an x value, if you will, of 9.138. And again, that's really just the most common question that's being asked. How long does it take to get to a certain value? Or, even more simply, what will the value of this function be when t is something like 10 or when t is 15? And then you can simply just plug this into your calculator and let t be 10, and it will spit out a number for you. So not terribly important in the big picture of our mathematics, but again, this is a kind of a cool function that handles things like the spread of a virus or the spread of a rumor, anything that's going to kind of be capped in its growth, even population. You could consider its growth to be capped at some point. So that's a pretty good summary on logarithmics and logistics.